If filtering makes your vector results feel random, you're not alone. We'll set up payload filters correctly and re-rank so filtered results still make sense. You might be filtering by category or date, and suddenly the top hits look unrelated. That happens when strict filters cut away vectors that carried contextual signals. Today, you will learn how to keep filters while restoring relevance by combining payload facets and a simple hybrid re-rank. You will see a clear pipeline you can reuse in search and recommendation tasks. I'm Professor Pi, teaching search and IR from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Qdrant Vector Search with payload filters and hybrid re-rank solves a common production problem. You want vector semantics, but you also need exact constraints. For example, find semantically similar product descriptions only from a specific brand or time window. Filters reduce noise, but they can also remove good semantic matches or surface weak matches that just meet the filter. Success means results that both satisfy constraints and read as relevant to users. The simple idea is two-step. First, ask Qdrant for vectors that meet the payload constraints. Second, adjust ranking by blending the vector similarity score with a fast keyword or metadata match. That way, you keep strict constraints and regain semantic ordering. Strength, precise control. Weakness, you add a small re-rank cost. We will build a tiny toy pipeline that creates a Qdrant collection, inserts 3 example vectors with payload facets, runs an unfiltered lookup, applies a filter, and then re-ranks the filtered results by mixing vector score with a keyword match. This keeps the code approachable and shows how to map it to larger systems. This snippet connects to Qdrant and creates a fresh collection. This snippet shows initializing the client and making a named collection with a vector configuration and distance metric. It starts by creating or resetting the collection, so we work from a clean state. The key lines allocate the vector size and choose the similarity measure, and the snippet registers the payload schema or leaves it flexible. Top to bottom, you see client creation, a safe delete or check, and then a create collection call. The important knobs here are the vector dimension and the distance choice, because they determine how Qdrant measures similarity and how stored vectors must be sized. Now we will add the toy data into that collection. This snippet writes 3 toy vectors with useful payload facets into Qdrant. This snippet builds 3 small semantic vectors and attaches payload keys like category, brand, or timestamp to each item. It then uses a bulk insert call to push vectors plus payload into the collection. The payload keys become the facets you will filter on later. The sequence shows assigning unique IDs, the vector embeddings, and the payload dictionaries. If you change the payload values, you change which documents match later filters. The example keeps the corpus tiny, so you can watch how filters change which items survive a query. Next, we will run a plain vector search without any filters. This snippet runs an unfiltered vector search in Qdrant for a small top K. This snippet performs a basic nearest neighbor query that returns the top few items by vector similarity only. It sends a query vector and requests a short list of results, and you see raw vector scores and payloads come back. The important lines are the query call and the top K argument, which controls how many candidates you consider. In real use, you might request a larger candidate set to give re-rank more options. But for this toy example, the small top K makes outputs easy to inspect. The returned vector score is the primary signal used before any filtering. Now we will constrain results by a payload facet. This snippet applies a payload filter in Qdrant to constrain results by facet. This snippet adds a filter object to the same vector query, so only items whose payload matches the constraint reach the result set. The filter could be an equals test on a category or a range on a date field. The code shows building the filter clause and passing it to the search call so that Qdrant applies the constraint server-side. The main behavior to note is that filtering can remove high-scoring vectors that do not match the facet. If the filter is too tight, you may get few or no matches. If it is broad, you retain more semantic options. Next, we will re-rank those filtered candidates with a hybrid score. This snippet re-ranks filtered Qdrant results by blending vector score with keyword match. This snippet takes the filtered hints returned by Qdrant and computes a secondary match score for each item. For example, a simple keyword overlap between the query text and the item title. It then combines the vector similarity and the keyword match into a blended score to reorder the items. The key lines show extracting the vector score, computing the keyword score, and using a weighted sum or multiplier to produce a final rank. The blend weight is the primary tuning knob here. Increase it to favor exact matches, decrease it to favor pure semantics. This toy flow maps directly to real systems. In a product search, you would request a larger candidate window from Qdrant to reduce false negatives. The keyword match could be a fast inverted index or a compact bag of words on the payload. The re-rank step runs in memory and adds only a small latency while dramatically improving perceived relevance when strict filters are required. Recap: Qdrant with payload filters gives precise constraints. Use hybrid re-rank when filters distort pure vector order. One caveat: re-rank adds compute and depends on the quality of your secondary signal. Next step: tune the blend weight between vector score and keyword match and measure result quality. Try different weights and track a relevance metric to pick the best trade-off. If short, practical IR helps, subscribe and watch the IR videos.